Okay, so this is the beginning of our polynomials topic, and we're going to start by looking at the most basic cubic and quartic graphs, and we're going to do that by extending our understanding of transformations that we've looked at in the context of many other graphs before now. So initially transformations of the parabola, and then we've applied those same transformations to hyperbolas and truncuses and square root graphs, etc. The same transformations apply in exactly the same way to the cubic and the quartic. So let's start with what the basic cubic and quartic shapes are, and then let's have a think about applying those transformations and then sketching some graphs. So y equals x cubed is pictured here on the left. You can plot out some points to see how we end up with this graph shape. For example, when x equals 0, y also equals 0, so we go through the origin. When x equals 1, 1 cubed is 1. When x equals 2, 2 cubed is 8. Okay, and obviously 3 cubed is 27, and so things get bigger and bigger and bigger as x gets bigger. When x equals -1, -1 cubed is going to still be -1. So unlike the parabola where -1 squared is +1, and we get the shape come back up here, the cubic is going to extend down into the bottom left quadrant of the Cartesian plane there. So when x equals -2, -2 all cubed is -8, etc. -3, when x equals -3, y equals -27. And so we get this cubic shape. Now the cubic introduces a new graph feature that we actually haven't talked about before now. This point here is called a point of inflection. Technically speaking, this is what we call a stationary point of inflection, and we'll talk a lot more about stationary points in second semester. But a stationary point is a point where the graph has zero gradient, and that is where if you were to draw the tangent to the graph at this point, it would be a horizontal line. Okay, you can have stationary points that are you can have points of inflection that are non-stationary points of inflection. So, for example, you can have a cubic that would have a shape like what I've just drawn in red here. It does have a point of inflection because by definition a point of inflection is actually a point where if you were to draw the tangent to the curve at that point, that is a straight line with the same gradient as the curve at that point, the tangent would cut through the graph there. Okay, so if you think about any other point on this cubic, sorry, I'm just trying to get rid of that. If you were to draw a tangent at this point, the tangent would sit totally below the graph at that point. Okay, it'll cut the graph somewhere down here, but that's not the definition. It's about it sitting on one side of the graph at the point of where it's tangent. So, if we were to draw a tangent down here, it would sit above the graph, whereas this point here, where the tangent cuts through the graph, is what is the definition of a point of inflection. So this is a point of inflection. It's a particular kind of point of inflection because the tangent would actually be a horizontal line, and therefore we have zero gradient at that point. The graph actually gets momentarily flat at that point. So the point of inflection is a really key feature of a cubic graph. If you're sketching a cubic of this shape, the point of inflection is a point that you must mark with coordinates. The quartic graph, so it's more like a parabola than the cubic graph in terms of it goes up, it stays above the x-axis at all times, or above or on the x-axis, and that's because of the even power. X to the power of 4, anything to an even power is always going to be positive, well, apart from 0. So our graph sits completely above the x-axis. So again, we could think through some points. When x equals 0, 0 to the power of 4 is 0. When x equals 1, 1 to the power of 4 is 1. When x equals 2, 2 to the power of 4 is 16. But on the left-hand side, when x is -1, -1 to the power of 4 is +1. So our graph comes back up again and we get this symmetry about the y-axis. Compared to the parabola, it's just a more extreme version. So if we were going to draw the parabola, it would also go through the origin, it would also go through -1, 1 and +1, 1, but it would only go through, 2, 4, -2, 4, 3, 9. So it's nowhere near as extreme in terms of its shape. Also, actually, between 0 and 1, the parabola would sit higher up than the quartic shape. And that's because if you were to think about, a fraction, say if x were to be a half, well, a half squared is a quarter. Whereas if we look at the quartic graph, a half to the power of 4 is 1/16. So this is going to be a lot lower down than the quadratic graph. And so that's where we get this more extreme shape with the quartic. Okay, between between -1 and 1, the graph is closer to the x-axis, and then after that it gets steep much more quickly, and so we get this more extreme kind of flat-bottomed shape. Okay, technically it doesn't have a perfectly flat bottom. If we were to zoom in here, you know, it would be only 0 gradient at the origin. It'd be, you know, sloped still, but it's less extreme in slope than a parabola. Just generally, while we're here, just thinking about further polynomial functions, if we were to think about y equals x to the power of 6, for example, it would be yet again a more extreme version of this shape. So it would be lower down here, and then it would be higher up here, more extreme this way. Okay, so we would just get more and more extreme shapes, but the same kind of shape. Similarly, if we were to look at y equals x to the power of 5, so the next odd degree polynomial, it would be lower down closer to the x-axis between 0 and 1. It would go through 1, 1 again, but then it would be steeper. Okay, so we just get more extreme versions of that same shape as we increase that power, x to the 7, x to the 9, x to the 11. So we're starting to build sort of idea about this big family of functions called polynomials. The other thing to note is not all cubic graphs are going to look like this particular shape. Okay, so this is a particular kind of cubic, and we're just going to look at these and these kinds of quartics in this initial stage, and then we'll build up some algebraic skills and some other skills that we need before we then look at some of the other varieties of what might happen with a cubic shape. So a cubic could also, rather than have one point of inflection, it could have 2 turning points. So it could take on a shape like that. As I mentioned also, its point of inflection doesn't have to be stationary, though those are a bit beyond the scope of the Maths Methods course. Okay. Quartic, there's even more things that could happen. So this sort of one single flat-bottomed turning point could instead be 3 separate, more like parabola turning points, if you like, so less flat, less extreme turning points. We could have one turning point and a point of inflection. It could be one turning point and a non-stationary point of inflection. So there's all sorts of different things that could happen. Might be the point of inflection that happens first and then the stationary point. So lots of different options, and as we increase the power of x, the variety of options that could occur only increases. So there's a lot that can happen here. We're really only going to be looking at a very small selection in this particular video, and when our polynomial function can be written in this form, this sort of turning point form that we're familiar with from our work with quadratic functions, then that will look like one of these shapes. Okay. Otherwise, but not unlike a quadratic, not every single cubic equation can be written in this form. Not every single quartic equation can be written in this sort of turning point form. Okay, so when it can be, those graphs will look like these shapes here. So we're just going to focus on those for this video. We'll expand our repertoire as we move through the topic. Okay, so we can apply our transformations to these graph shapes in the same way that we've applied them to all the other graph shapes we've looked at before now. So we know that if we have a function f of x and we want to dilate it by a factor of a from the x-axis, we multiply that whole function by a. So in the case of the cubic, that would give the equation y equals ax cubed. That would be the cubic shape, so this shape up here, dilated by a factor of a from the x-axis. So for example, if we were drawing y equals 2x cubed up here, all of the y values would be multiplied by 2. So instead of going through the 0.11, we're now going to go through the 0.12. Instead of going through 2.8, we now go through 2.16. Okay, so we get a much more extreme, stretched away from the x-axis cubic shape. Okay. Similarly for the quartic, dilating by a factor of a from the x-axis, y equals a times x to the power of 4. Okay, so multiplying the whole function by a. We know we can reflect these shapes in the x-axis by making the whole function negative, so multiplying the whole function by -1. So in the case of the cubic, that's y equals negative x cubed. In the case of the quartic, that's y equals negative x to the 4. So negative x cubed, if we were to take this cubic shape and reflect it in the x-axis, it's instead going to be going this way. If we were to take this quartic shape and reflect it in the x-axis, it's instead going to be going this way. Translation to the right by h units is when we have f of x minus h. So remember, inside the function, subtracting h to move to the right. Okay, so our cubic function, that would be replacing just the x part of the function with x minus h. So we get x minus h all cubed, and for the quartic, obviously, x minus h all to the power of 4. Translating up by k units, we add k onto the end of the function. So y equals x cubed plus k is going to go up by k units, or y equals x to the 4 plus k is going to be the quartic moved up by 4 units. So much like the parabola, the turning point or the point of inflection is a key feature of the graph. So if we move this graph to the right by 3 and up by 9, for example, and so the turning point is up there, that's going to have equation y equals a times x minus 3. There's to the right by 3, power of 4, and up by 9. Okay, so this is our turning point still. In the case of the cubic, it's not technically a turning point, it's a point of inflection, but all the same, those h and k values, those translations left, right, and up and down, are going to tell you where the point of inflection ends up. And obviously those transformations can all be combined together. A cubic with dilation and reflection caused by changing translation to the right by changing h, and then translation up by k, and the same with the quartic. So we can think about this as being sort of turning point form. In the case of the quartic, it's still turning point form. In the case of the cubic, I guess it's more point of inflection form. So whenever the cubic or quartic function is given in this form, and bearing in mind that any one of those values could be 0. So for example, a graph of this, without a k, so that's still in turning point form. It just hasn't gone up or down. Okay, a graph, for example, a cubic graph, for example, without an h, that hasn't gone left or right, but it's just gone up and been dilated. So any of those values apart from a, h, or k could be 0, and it's still in turning point or point of inflection form. Now, as we know, we have talked about two other transformations, reflection in the y-axis and dilation from the y-axis. So in the case of these functions, we actually don't really need to consider those as separate transformations, because if we were to take the quartic graph and reflect it in the y-axis, which would mean replacing just the x part of the function with negative x, that's just the same as x to the power of 4. And we could see graphically, if we were to reflect this shape in the y-axis, it's going to still be the same shape. So we don't need to consider reflecting in the y-axis for the quartic. In the case of the cubic, reflecting in the y-axis is negative x all cubed, which is just the same as negative x cubed, which is the same as reflecting in the x-axis. So if we reflect this graph in the y-axis, we actually get the same graph as if we had reflected in the x-axis. Okay, so again, we don't need to consider the y-axis reflection as something separate when we're looking at these basic cubic and quartic shapes. Similarly, the dilations from the y-axis, any dilation in this direction, we can just explain it as a dilation in this direction instead. So, for example, if we have a dilation by a factor of 1/2 from the y-axis, which would be this function here. Remember, it's the reciprocal of that value inside the function, so that's dilating by 1/2 from the y-axis, which means all of the the x values get halved, so the graph is going to get squashed in, and we would get a graph closer to the y-axis. We can instead expand this out as 2 to the power of 4 is 16, x to the power of 4. So actually it's the same as taking our original graph and dilating it by 16 from the x-axis. So we don't need to think about the y-axis dilation separately. We could always just expand those functions out and think of them as x-axis dilations. Okay, so that's what's talked through in those two sentences here. The dilations from the y-axis and reflections in the y-axis still work in the same way for these functions, but we actually don't really need to worry about them with these functions because we can think about those transformations in other ways. Okay, so let's get into sketching some graphs. Sketch the graphs of y equals 4x cubed, y equals x cubed, and y equals 1/4 x cubed. Okay, so they're all cubic functions, just with 3 different dilation factors. So let's draw this basic cubic function first. Let's draw that, and then let's draw in the dilated versions. Let's think a little bit about sort of scale, given we want to draw quite a few 3 different graphs on the same axis. So 1, 2, 3, 4. 1, 2. Actually, no, it's okay. Okay, so if we were to draw the cubic, y equals x cubed, the basic cubic, point of inflection at the origin, it goes through 1, 1 and negative 1, 1. It would go through 2, 8, which is going to be way up there, and negative 2, 8, which is going to be way down there. So this is going to give us a sense of the shape. Okay, so that's going to be y equals x cubed. Now the other one we want to draw, one of the others we want to draw is y equals 4x cubed. So instead of going through, that's going to be a dilation by a factor of 4 from the x-axis. So instead of going through 1, 1, it's going to go through 1, 4, and 1, negative 4. So a same shape but stretched away from the x-axis by a factor of 4 is going to look something like that. And then the 1/4 x cubed is the cubic graph dilated by a factor of 1/4 from the x-axis. So instead of going through 1, 1, we're going to be going through 1, 1/4 and -1, -1/4. You might also remember the original cubic goes through 2, 8. So 1/4 of 8 is 2. So this graph is going to go through 2, 2 and -2, -2. So that's y equals 1/4 x cubed. So in terms of sketching these graphs, we do need to have at least one point marked on them. They obviously all go through the origin, but we can't tell exactly what they are without a point. So I'm going to mark that point 1, 1/4. I'm going to mark this point as 1, 1. And let's mark this one up here at 1, 4 to give us that sense of dilation. So really, the dilation's the last thing you would worry about when you're sketching a graph. Usually, any dilation factor would be accounted for when you go about calculating any points on the graph. But when you've got more than one graph on the same axis, it's important that you've got some meaningful sense of scale so that it's clear how they're different to each other. Okay. All right, and as always, point of inflection, but in this case it's the origin, so we don't technically need to mark it, but we can. Point of inflection marked, and at least one other point marked on the graph. All axis intercepts should always be marked. So that's why we needed to add on the extra point, because our point of inflection was the only axis intercept for these three graphs. Okay, let's draw the next one. Sketch the graph of y equals x plus 3 to the power of 4 plus 4. So the first thing I'm looking at is that it's a quartic. Okay. It's a quartic equation in this turning point form, so I know it's going to be this kind of flat-bottomed parabola shape. It's not a parabola, but just for reference for something we're more familiar with. So then the x plus 3 in the bracket, that's a translation to the left by 3, and then the plus 4 on the end is up by 4. And so that means that our turning point, and the quartic does have a turning point, is at -3, 4. So we haven't got any reflection. So the turning point is going to be sort of up over here, and it's going to go this way. So we're not going to be crossing the x-axis, but we will cross the y-axis. So we need to work out our y-intercept. Let's do that. Y-intercept, let x equal 0. Okay, so y equals 3 to the power of 4, that's 81. Plus 4, so the y-intercept is at 85. Okay, so it's going to be hard to get exactly precise sort of scale here, but you do certainly want to give a sense that your y-intercept is quite large compared to where your turning point is, sorry. So I'm going to mark my turning point here. I'm going to draw in. You also want to try and give a bit of a sense that you've got that kind of flat-bottomed shape, even though technically it's not flat for any more than a moment. You just want it to not look like a parabola. So my y-intercept is at 0.85. My turning point is at -3, 4. At least 2 points, including the turning point. So we're all done. Okay, example 3. Sketch the graph of y equals 1/2 x minus 1 all cubed plus 4. So it's a cubic. It's in this sort of turning point / point of inflection form, so we know it's going to be this kind of shape. We've got a dilation by a factor of 1/2 from the x-axis. So that's just going to be wider and flatter, but without drawing another cubic on the same axis. It's hard to show that. So it'll be the points that we calculate that will show that. We can see that we've gone to the right by 1 and up by 4. So our turning point is at 1, 4. And we're going to need to calculate x and y intercepts. So the cubic, if our turning point's at 1, 4, we'll definitely be crossing both axes. Crossing both axes, whether it's here and here or whether it's actually up here and here. So we definitely need to calculate those before we go ahead and draw anything. So our y-intercept, we let x equal 0, so y equals half 0 minus 1, so -1 cubed plus 4. -1 cubed is -1, so -1 times a half is -1/2 plus 4. So it's 4 minus a half, which is 3.5, or 7 on 2. And then our x-intercept, we let y equal 0. 0 equals half x minus 1 cubed plus 4. We'll spend quite a lot of time looking at solving cubic equations, but in these particular turning point form or point of inflection form, it's a nice easy solve just by doing the same thing to both sides until we get x on its own. So in this case, we're going to subtract 4 from both sides. And then the opposite of multiplying by a half is to divide by half, which is to multiply by 2. So we're doubling both sides. That's a common error students make. They really struggle when there's a half here that they're trying to undo. The opposite of halving something is not to halve it again. It's to double it. So negative 8 equals x minus 1 cubed. Then we're taking the cube root. So x minus 1 is the cube root of negative 8. So we can cube root a negative, okay? It's going to give us a negative, and the cube root of 8 is 2, so it's negative 2. Now notice you don't get plus or minus when you take a cube root, and that's because if you have negative 2 cubed, it is negative 8. But if you have positive 2 cubed, it's not positive or it's also positive 8. Sorry, it's positive 8. So therefore, the cube root of positive 8 isn't plus or minus 2, it's only positive 2. Whereas the cube root of negative 8 isn't plus or minus 2, it has to be negative 2. So when it's an odd root, cube root, fifth root, seventh root, etc., it won't give you a plus minus. It's only when it's an even root. Okay, so x minus 1 equals negative 2, so x equals 1 minus 2, which is going to be negative 1. Okay, so we've got our y-intercept and our x-intercept and our turning point. So just thinking a bit about sort of scale, where things need to be. Okay, so negative 1, positive 1. And then let's go with, no, I won't make it that big, be off the page, 1, 2, 3, 4. So my point of inflection is at 1, 4. My y-intercept is at 3.5, 7 on 2, which is going to be there. So again, thinking a bit about the scale, it doesn't need to be perfect, but you don't want to have your y-intercept happening down here somewhere. You need to be consistent that it's actually quite close to where the turning point is, the point of inflection is, sorry. And your x-intercept is at negative 1. You might choose to mark some sort of symmetrical points here. So if, for example, across by 1 and down by a half, across by 1 and up by a half, just to give you a rough guide as to where your shape should go. Again, sort of across by 2 and down by 4, across by 2 and up by 4 sort of thing, just gives you a rough, even if you don't mark the points, but you're just sort of eyeballing them when you're thinking about the shape. It'll just help you get a more symmetric kind of shape. Okay, so there's our cubic, point of inflection marked, y-intercept marked, and x-intercept marked. Okay, so fairly straightforward, nothing particular about sketching graphs of this form with your CAS. It is possible to use your CAS to find a point of inflection, so if we sketch the one we just did here with our CAS, if we look at half x minus 1 cubed plus 4, we draw that with our CAS, we get what we've drawn on the paper there. Obviously you can make adjustments to your window as is relevant, so you can see what's happening a bit better. You can get your CAS, obviously in this format it's easy to see where the point of inflection is from the equation, but menu 6 for analyze graph and 5 for inflection will find the coordinates of that point of inflection for you at 1, 4. So just given that's a new graph shape, just something to be aware of. Okay, some practice in exercises 6E and 6I.